myself, Escotilla, from Department of Chemical Engineering, Minerals and Engineering College. Today I'm going to handle the subject chemical process calculations and the session of material balances. This is the chapter 3 in chemical process calculations. Now today I'm going to handle first part in the material balance. The main objective studying material balances, students will be able to identify the types of processes, that is batch, semi-batch and continuous processes. Students will be able to perform degree of freedom analysis. Students will be able to perform material balance of single unit, multiple unit, non-reactive processes under steady state condition. Process classification. There are three types of processes. First one is batch process. Feed is in this process. Feed is charged to the process, and the product is removed. When the process is completed. Here, no mass is fed or removed from from the process during the operation. It is used for small scale production. It is operated in unsteady state. Next, continuous process. Input and output flow is continuously throughout the duration of the process. Operation is steady state and it is used for large scale production. Next, semi-batch process. Neither batch nor continuous. During the process, a part of the reactant can be fed or a part of the product can be removed. Operation is unsteady state. What is steady state and what is unsteady state? In steady state, all the variables, that is temperature, pressure, volume, fluid, etc., do not change with respect to time. Example, continuous process. There will be minor fluctuation that can be acceptable, and unsteady state or transient state. It is the process variable that changes with time in a particular mass flow. Example, batch and semi-batch. Define type and operation of the process below. Discussed yourself. A balloon is filled with air at steady state of 2 grams per minute. A bottle of milk is taken from the refrigerator and left on the kitchen. Water is boiled in open flask. We have to find what type and operation of the process. First is a balloon is filled with air at steady rate of 2 grams per minute. It is semi-batch and unsteady state. And a bottle of milk is taken from the refrigerator and left on the kitchen. That is batch and unsteady state. Next, water is boiled in open fat. This is semi-batch and unsteady state. Next, general balances. A balance on a conserved quantity, which is total mass property plus species energy momentum in a system. A system is a single process unit, a collection of units, or an entire process. May be written in the following way. That is, input plus generation minus output minus consumption is equal to accumulation. Input is what is entering through the system through boundaries, and generation is produced within the system, and output is the product or leaving through the system boundaries. If consumption is consumed within the system and accumulation is built up within the system. It's what is differential and integral balances. Two types of balances in Newton. First one is differential balances. Balances that include what is happening in a system at an instant time. Balance equation is a rate of input, rate of generation, etc., and has no units of the balanced quantity unit divided by a time unit. Usually applied to a continuous process. Its integral balances. Balances that describe what happens between two instances of time. Balance equation is an unit of the balanced quantity and has a corresponding unit. It is usually applied to a batch process with the two instances of time being the moment after the input takes place and the momentum before the product is returned. Simplify group and mass balance with the balanced quantity, that is total mass, set generation is equal to 0 and consumption is equal to 0. Mass can neither be created nor be destroyed. If the balance of substances is a non-reactive species, it is neither a reactant nor a product. Then set generation is equal to 0 and consumption is equal to 0. If the consumption is at steady state, set accumulation is equal to 0, regardless of what is being balanced. Next, balances in continuous steady-state process. General mass balance equation is input plus generation minus output minus consumption is equal to accumulation. A steady state accumulation will be equal to 0. Then the general mass balance equation becomes general plus sorry, input plus generation minus output minus consumption is equal to 0. If the balance on non-reactive pressures or total mass balance equation becomes generation is equal to consumption equal to 0. Then the general mass balance equation will be input equal to output. For non-reactive processes, what is non-reactive process? The process that undergoes without chemical reaction is known as non-reactive processes. Depends on the physical or environmental factors like temperature, volume, and pressure. Non-reactive processes can be physical. Chemical balance on a continuous distillation process. It is an example. A solution is 1000 kilogram per hour of a mixture of benzene and toluene containing 50 percentage benzene biomass is separated by distillation into two fractions. The mass flow rate of the benzene in the top of the stream is 450 kg and the toluene in the bottom stream is about 475 kilogram per hour. This operation is a steady state. Type balances on benzene and toluene to calculate the unknown component fluids in the output streams. The process can be depicted schematically as follows. Next, the equipment name is distillation. The process is distillation. Here they have given that 50 percentage of benzene is mass separated by distillation into two fractions, and the top flow rate is given and the toluene bottom flow rate is given. You have to assume the basis of 1000 kilogram per hour, and it is given that 50 percentage is benzene and 50 percentage is toluene. So 500 kilogram per hour and 500 kilogram per hour of toluene. Next, they have given the top product is 450 kilogram benzene per hour and the bottom product is 475 kilogram toluene per hour. Since the process is in steady state, there can be no buildup of anything in the system. So the accumulation term equals to 0 in all material balances. In addition, since there is no chemical reaction occur, there can be no non-zero generation or consumption terms. For all balances, take the simplest form, input is equal to output. First we have to first we have to make the benzene balance. That is input is equal to output. Our input is 500 kilogram benzene per hour and output in the bottom product. That is top product is 500 kilogram per hour and there will be some amount of benzene in the top bottom product also that is considered as input. Based on this M2 is given as 50 kilogram benzene per hour. With toluene balance, input is equal to 500 kg benzene per hour and which is equal to 475 kg V per H. That is the output in the bottom product plus amount of toluene in the top product is considered as M1. On simplifying this, M1 is equal to 25 kg T per hour. Check the calculation. You have to find the mass balance, total mass balance. That is 1000 kg per hour is equal to 450 plus 475 plus M1 plus M2. We have found that M1 and M2 by benzene balance and bromine balance. Based on that, we have to check that the amount we have found is correct or not. Integral balances on batch processes. Ammonia is produced from nitrogen and hydrogen in a batch reactor. At the time T is equal to 0, there are N naught mole of ammonia in the reactor. And at the later time Tf, the reaction terminates and the contents of the reactor, which include enough ammonia are withdrawn. Between T naught and Tf, no ammonia enters and leaves through the reactor boundaries. We know the general mass balance equation is equal to input plus output plus generation plus accumulation. So consumption is equal to accumulation. For general mass balance equation, input is equal to 0 and output equal to 0. Generation minus consumption is equal to accumulation. For batch reaction, accumulation is equal to final minus input. And for general material balance for batch processes, initial input plus generation is equal to final output plus consumption. This is an example of a batch mixing process. Two methanol water mixtures are contained in a separate glass. The first mixture contains about 40.08% of methanol, and the second contains 70.02% methanol. If 200 grams of the first mixture is combined with 150 grams of the second, what are the mass composition of the glass? We have given the input of 200 grams and 150 grams. What we have to find is mass and composition stream of the product. To find the composition stream of the product, we have to do the individual material balance and to find the total mass of the product. We have to calculate from the overall material balance. Here, this is the schematic diagram. We have given with 0.4 gram of methanol and 0.6 gram of water, totally 200 grams. Next, next is 0.7 percentage of CH2OH and 0.3 percentage of H2. On simplifying this, we get C3OH 1 minus H2. Observe that the input and output side shows on the chart denote the initial and final states for the batch processes. Since no reactions are involved, the general and the consumption may be omitted so that the oil balances in the simplest form. Input is equal to output. Total mass balance is equal to 100 kg equal to m. And adding this, we get m is equal to 50 gram. Next to methanol balance. So 200 gram is 0.4 gram of methanol and 50 gram is equal to 0.7 gram of methanol and which is equal to gram CH3OH. On simplifying this, we will get m is equal to 350 grams. So m is equal to 3.529 gram into CH3OH. Calculation. Water balance is equal to input plus output. Input is equal to 2000 plus 0.6 plus output. Input is equal to 200 into 0.6 plus 150 into 0.3, which is equal to 300 into 1 minus 0.529. On simplifying this, we will get 160 gram of water is equal to 160 gram of water. The internal balances on semi-batch processes. Air is bubbled through a drum of liquid hexane at a rate of 0.1 kmol per minute. The gas stream leaving the drum contains 10.0 mole percentage hexane vapor. Air may be considered insoluble in liquid hexane. Use an integral balance to estimate the time required to vaporize 10.0 meter cube of the liquid. This is an estimated schematic diagram, that is input is 0.1 kilomole air per minute and output is 0.1 kilomole C2 CCH14 kilomole and 0.9 kilomole air per kilomole. We begin with the differential balance on air. Since we assume that air neither dissolves in liquid, accumulation is equal to zero. Not rich with hexane in the process unit, generation is equal to accumulation is equal to zero. The balance reduces to input is equal to output. 0.1 kilomole air per minute is equal to 0.9 kilomole air per minute, which is we all simplify this, we will get n is equal to 0.11 kilomole per minute. Integral hexane balance. Proceeding from time t is equal to 0 to t is equal to t is equal to 0 to t is equal to t minimum, the time we seek to calculate. The balance has the form accumulation is equal to output. The accumulation term, which is the total change in the moles of the liquid hexane in the system during the time Tf must be negative. Since hence hexane is being lost from the system, since the total number of moles of hexane evaporated occupied a liquid volume of 10.0 meter and the specific gravity of the liquid hexane is 0.659. The accumulation terms del n is equal to minus 10.0 meter cube into 0.659 kilogram per liter into 10 to the power of 3 into 1 kilomole divided by 86.2, which is equal to minus 76.25 kilomole of hexane. The output term in the balance is the rate at which hexane is leaving the stream, that is 0.1 n kilomole hexane per minute times the process limit Tf minute. The balance is accumulation minus the input is equal. Therefore, minus 76.45 kilomole of hexane, which is equal to 0.00 mgd. So that n is equal to 0.111 kilomole per minute. From this, Gt is equal to 6,880 minutes. This flowchart in your given process information has to determine something about the process, organize the information in a way that is easy for subsequent calculation. The best way is to draw a flowchart using process or other symbols to represent process units, reactor, mixer, separation units, etc. Lines with arrows to represent the input and outputs. Exposure of a process can help in regular balance calculation, started and keep them moving. Flowchart must be fully labeled when it is first designed. The values of the known process variables and the symbols for unknown variables will be written for each input and output. The flowchart will function as a scoreboard for the problem solution as each unknown variable is determined its values is filled in so that the flowchart provides a continuous record of where the solution stands and what must still be done. Next flowchart will be write the values and units for all known stream variables of the locations presented on the flowchart. For example, a stream containing 21 mole of O2 and 79 percentage of PO2 and 320 percentage 320 degrees Celsius and 1.4 atmosphere flowing at the uh, rate of 400 mole per hour might be labeled 400 mole per hour and 0.21 mole oxygen per mole and 0.79 nitrogen per mole and temperature is equal to 320 and pressure is equal to 1.4. As flowchart labeling, process stream can be given in cubics as the total amount of flow rate of the stream and the fractions of each component. Versus 60 kilomole of N2 per minute and 40 kilomole of O2 per minute. That is also equal to 100 kilomole per minute is equal to 0.6 kilomole nitrogen per kilomole and 0.4 kilomole of O2 per kilomole. Or the Ampere has the amount of flow rate of each component as 3 lbm CH4, 4 lbm C2H4, and 3 lbm C2H6, which is also similar to 10 lbm, that is 0.3 lbm C2H4 per lbm, 0.4 lbm C2H4 per lbm, and 0.3 lbm is equal to C2H5 per lbm. Flowchart an experiment the growth rate of certain organisms requires an improvement of phematide and enriched in oxygen. Three inputs change are fed into an aeration chamber to produce an output stream with the desired composition. First, liquid water fed at the rate of 20 centimeters per minute, air at the rate of 21 percentage and 78 percentage N. Pure water with the mole flow rate one-fifth of the molar flow rate at stream. The output gas is analyzed and is found to contain 0.15 1.5 mole percentage of water. Draw and label the flowchart of the process and calculate the downstream variables. The flowchart that contains evaporation output is 0.2 N2 mole O2 per minute and mole per minute, 0.21 mole of oxygen per mole, 0.79 mole of nitrogen per mole, and the output is N3 mole per mole is 0.015 mole water per mole and Y mole oxygen per mole that is equal to 0.985 minus Y mole nitrogen per mole. When and the steam that is entering is 20 centimeter cube water that is liquid per minute which is represented as N3 mole water per minute. Notes on the reading since the one known flow rate 20 centimeter cube water per minute is given on a per minute basis. It is most convenient to label all the stream flow rates on this basis. Once the variable N1 is chosen for the asteroid, the given information about the ratio of different O2 flow rates may be used to label the O2 flow rate 0.2 N1. The mole fraction of the component of any stream must add up to Since the mole fraction of water in the outlet stream is known to be 0.015, means the mole fraction of water is created by the total N2 must be 1 minus 0.015 minus y, which is equal to 0.985 minus y mole of nitrogen per there is a simplified schematic diagram of the evaporator. The quantity N2 may be calculated from the given volumetric flow rate, and the density of the liquid water, that is the absorption rate, and one is equal to centimeter to water into 1 gram of water per centimeter into 1 mole of divided by 18 potential. So that N2 is equal to 1.11 mole water per minute. The three remaining unknowns N1, N3 and Y may be determined from balances, all of which have the simple form N2 is equal to O2 for the non-reactive steady-state process. The balances of state are easily done by referring to the flowchart. Water balances N1, that is mole water per minute, which is equal to N2 mole per minute into 0.015 mole water per minute. From that, N1 is equal to 1.11 mole per minute and N1 is equal to 74.1 mole per minute. Its N2 balance N1 mole per minute into 0.79 mole N2 per minute, which is equal to N3 mole per minute into 0.985 minus y into mole N2 divided by mole. Upon simplifying this, we will get N1 is equal to 60.8 mole per minute and N1 is equal to N3 is equal to 74.1 mole per minute. From this, we can determine that y is equal to 0.337 mole oxygen per mole. From the total mole balance, 0.2 N1 plus N1 plus N2, which is equal to N3. N2 is equal to 1.11 mole per minute and N3 is equal to 74.1 mole per minute. From this, N1 is equal to 60.8 mole per minute. Its flowcharts labeling, if the mass of stream 1 is half that of a stream 2, label the masses of these streams as M and 2 rather than M1 and M2. If you know that the mass fraction of nitrogen is 3 times that oxygen, label mass fractions as Y gram oxygen per gram and 3 gram of nitrogen per gram rather than Y1 and Y2. When labeling component mass fraction or mole fraction, the last one must be 1 minus the sum of the others. If volumetric flow rate of a stream is given, it is generally useful to label that mass or molar flow rate of a stream or to calculate it directly since balance are not written on volumetric quantities. Consistent on notation. M is the mass and m dot is mass flow rate, n is moles, n dot is molar flow rate, and v is volume, and v dot is volume flow rate. X is the component fraction in liquid, and y is the mole fraction in gas. Flowchart scaling and basis of calculation. Flowchart scaling, that is the procedure of changing the values of all stream amounts or flow rates by a proportional amount while leaving the stream composition unchanged. The process would still be balanced. Scaling, if final stream quantities are larger than the original quantities, Scaling down if final stream quantities are smaller than the original quantities. Next, flowchart scaling and basis of calculation. 1 kilogram C6H6 that is gives 2 kg. In 1 kilogram C7H8 is 0.5 kg C6H6 per kg and 0.5 kg C7H8 per kg into 300. If it is multiplied by 300 means 300 kg of C6H6 and 300 kg of C7H8, which gives 600 kg divided by, for it contains zero point 0.5 kg C6H6 per kg and 0.5 kg C7H8 per kg. If we are replacing the kg with the kg per hour, it will be converted to 300 lbm per hour, and the product is 600 lbm per hour. Suppose you have balanced a process and the amount of flow rate of one of the process stream is N1, you can scale the flowchart to make the amount of flow rate of the stream N2 by multiplying all streams is N1. You can scale the flowchart to make the amount of flow rate of the stream N2 by multiplying all streams amount or flow rate by the ratio N2 by N1. Scaling factor is equal to desired amount divided by old amount. You cannot overscale masses or mass flow rates to molar quantities or vice versa by simple multiplication. Conversions of this type must be carried out using the methods as discussed in mass fraction and mole fraction section. Example scale up of a separation flowchart. A 60 to 40 mixture by moles of A and B is separated into two fractions. A flowchart of the process is given. The input is 100 mole, that is the basis, 0.60 mole A per mole and 0.40 mole per B. Our output is 50 moles per each, and then 0.95 mole A per mole and 0.05 mole B per mole. And the bottom product is 12.5 mole A and 37.5 mole B. It is desired to achieve the same separation with the continuous speed of 1250 pound moles per hour. Scale the flowchart accordingly. The scale factor is 1250 lb moles per hour per 100 mole. So 12.5 lb moles per hour per mole. The masses of all streams in the batch process are converted to flow rates as follows: 100 mole into 12.5 lb moles per hour per mole, which is equal to 1250 lb moles per hour. Top product stream, that is 50 into 12.5 is equal to 625 lb moles per hour, and bottom product is 12.5 into 12.5, which is equal to 156 lb moles A per hour. 37.5 into 12.5 is equal to 469 lb moles B per hour. The units of the mole fraction in the top product stream may be changed from mole per mole to lb mole per lb mole, but their values remain the same. The flowchart of the scaled up process as follows. Balancing a process: 3 kg per minute of benzene and 1 kg per minute of chlorine are mixed. Two unknown quantities, that is m and x, associated with the process, so two equations are needed to calculate. For non-reactive steady-state process, input is equal to output. Three possible balances can be written: balance on total mass, balance on benzene, and balance on chlorine. Any of two which provide the equation needed to determine index. For example, total mass balance m kilograms 3 kilogram per minute plus 1 kilogram per minute is equal to m kilogram per minute. From this we can calculate m is equal to 4 kilogram per minute. And benzene balance is 3 kilogram of benzene as input and 4 kilogram of benzene as output, that is equal to x. From that x we can find x from this equation 0.75 kg benzene per kg. Each balance is used when a choice exists and the order in which the balances should be written. Rules of thumb for non-reactive processes. The maximum number of independent equations that can be derived by writing balances on a non-reactive system equals the number of chemical species in the input and output streams. Write the balances first that involve the fewest unknown variables. Basics of a calculation. Balanced processes can always be split, meaning that material balance calculation can be performed on the basis of any convenient set of stream amount of flow rate and the results can afterward be scaled to be desired extent. A basis of calculation is an amount of flow rate, that is mass or molar, of one stream or stream component in a process. All unknown variables are determined to be consistent with the basis. If the stream amount of fluoride is given in the problem, choose this quantity as a basis. If no stream amount of fluoride are known, assume one stream with known composition. If mass fraction is known, choose total mass or mass flow rate as basis. If mole fraction is known, choose the total moles or molar flow rate as basis. Balancing on mixing unit. An aqueous solution of NaOH contains 20% of NaOH by mass. It is desired to produce an 80% NaOH solution, 8% NaOH solution by diluting a stream of the 20% solution with a stream of pure water. Calculate the ratios in liters water per kg feed solution and kg product solution per kg feed solution. Choose a basis of calculation and amount of flow rate of one of the feed or product streams and then draw and label the flowchart. We will arbitrarily choose a basis of 100 kg of the 20% feed solution. We could also have chosen a flow rate of 100 lbm per minute of the 8% product solution or 10 tons of diluent water. The final results do not depend on the basis chosen since we are only asked to find ratios of stream units. The flowchart appears as follows. Our input is 100 kg in that 0.2 kg NaOH per kg and 0.8 kg water. And the mixer diluent is N1 and V1 in liters. And N2 is our product in that it contains 0.08 kg of NaOH and 0.922 kg of water. Thus, total input is equal to output. Total mass balance is therefore given with an input of 100 kg and water is V1 ml and which is equal to N2. NaOH balance input is 0.2 kg NaOH into 100 kg and our output is 0.08 kg of NaOH into M2. From this you can find M2 is equal to 250 kg of NaOH. From this we can find that M1, that is total balance is equal to 100 kg plus M1 is equal to M2. From the M1 we can find that the amount of water that is taken as a diluent as 150 kg per diluent water equivalent. Although we are not given the temperature or pressure at which the mixing is done, the density of liquid water is approximately constant is 1 kg per liter. So V is equal to 150 into 1 kg per liter, which is equal to 150 liters. The ratios requested in problem statement: a ratio liter water per kg feed solution and kg product solution per kg feed solution. V1 divided by 100 kg is equal to 1.50 water per kg of feed solution. M2 per 100 kg is equal to 2.50 product solution by kg feed solution. Degree of freedom. Before doing any material balance calculation, we use a properly drawn and labeled flowchart to determine whether there is enough information to solve the given problem. The procedure for doing so is referred to as degree of freedom analysis. Procedure to perform a degree of freedom analysis. Draw and completely label a flowchart. Count the unknown variables on the chart, that is n unknowns. Next, count the independent equations, that is n independent equation. Find number of degrees of freedom, that is NDF. NDF is equal to n unknowns minus n independent equations. Next, number of degree of freedom. Three possibilities, number of degree of freedom. If NDF is equal to 0, problem can in principle to be solved. And if df is greater than 0, there are more unknowns than independent equation. Relating to them, at least NDF additional values must be specified before remaining variables values can be determined. Either equations have been overloaded or the problem is unspecified. If n is less than 0, there are more independent equations than unknowns. Either flowchart is incompletely written or the problem is overspecified with redundant or possibly inconsistent equations. There is little point wasting time trying to solve the balance for NDF greater than 0 or NDT less than 0. Next, sources of balance or source of equation for balance, material balance and energy balance, process specification and problem statement specify process variables, physical properties, laws, equation of state for gases, etc. And physical constraint with the mode reactions of the three components of the stream or label XA, XB, XC, the relation among these variables is XA plus XB plus XC is equal to 1. Then the procedures for equal to process material balance calculation. Choose the basis of calculation and note the loading for one of the process streams. Draw a flowchart and fill in all unknown variables, including the basis of calculations. Then label unknown stream variables on the chart. Express what the problem statement asks you to determine in terms of your given variables. If you are given fixed mass and the mole units for a stream, such as the total mass flow rate and component mass fractions or vice versa, convert all the quantities to quantities. Do the degree of freedom analysis. If the number of unknowns equal the number of equations relating the system has zero degree of freedom, write the equations in an efficient order, minimizing subatomic equations and circle the variables for which you can solve. Solve the equations. Calculate the quantities requested in the problem statement. They have not already been calculated. If a stream quantity or flow rate entry was given in a problem statement and another value NG was neither chosen as the basis or calculated for the stream, can scale the balanced process by the ratio NG by NC to obtain the final result. Balances or multiple human processes. In real chemical industries, more than one unit process exists, such as separation, actor, reactor, and so on. Need to note term called system in order to solve a material problem. System. Any proportion of process that can be enclosed within a hypothetical box. It can be the entire process or interconnected of process unit. A single unit a point which two or more stream come together into one stream or etc. The inputs and the outputs to a system are the process streams that are intersect with the system is the system of unit process in this A, B, C, D, and E are the five unit processes that is involved in the system. balances on multiple balances on multiple unit processes. Solving material balance in multiple unit process is basically the same as a single unit process. In multiple unit must isolate and write balances on several subsystems to obtain enough equation to determine what unknown string variables. Always perform degree of freedom analysis before solving a material balance of a system. Balance on two-unit process. A labeled flowchart of a continuous steady-state two-unit process is shown below. Each stream contains two components, A and B, in different proportions. Three streams whose flow rates and compositions of hot mode are labeled as 1 and 2. Calculate the unknown flow rate from the composition of the stream 1, 2, and 3. We have given with the basis flow rates. The system above which might be written on the same following representation on the chart. The outer boundary encompasses the entire process and has the input and output streams of all the streams that enter and leave the processes. Two of the interior boundaries surround individual process units, and the third encloses a stream junction